So what shall we do today?
We have some doubts in the assignment.
Okay. Let me see if I can answer, because I gave the problems. I haven't looked too much at the problems myself. Yeah, which problem?
A9, second one.
Okay.
He said destroy operands. So, like, does he mean removing them, or what did he mean?
No, destroy operand meaning, see, if you look at if you look at the stack architecture, like it basically replaces the top of the stack, isn't it?
Yes, ma'am.
So then in the accumulator, anyway, see, if you have a 3-register sort of an instruction, then you have 2 operands and the result is stored in the 3rd register. But if you have a 2-register instruction format, one of the registers is both the source and, I mean, it's like the input-output parameter I used to keep talking about in your programming course, right?
Yes,
So that's what he means when he says the operand is destroyed, because its data is lost. You're storing the result in it. So the original input value is gone.
Okay.
So in the stack and accumulator, you have that problem, right?
Yes, ma'am.
So
Okay, destroy in the sense like if we take this to
the value is no longer available. That's what it means. The input value. Yeah.
Okay.
Yeah, I didn't read this thing completely. I looked at it. I thought it's an interesting question. It's marked also that it is not very difficult. So I decided, I was looking at problems which are not difficult, right? That's what I said. I'm not giving anything which is marked even 20 most of the time. One of the things in architecture is the questions are very long. You have to really spend time understanding the questions. Answers are very short. And those are favorite questions as you go into higher education, actually.
Ma'am, I do have some questions for the coming up portions.
Okay. Actually, regarding your last week's class also, I've been breaking my brain. That question you asked, why can't it continue to process reads while doing write back? Why do you need a write buffer? You asked that question, right, last time. So I have been thinking more about it, and this is my explanation. Unfortunately, I have no idea whether I'm right or wrong. Maybe Rukma also can pitch in. Like, actually, if you say write back, right, what is happening? You're reading from the cache and writing into main memory. Right?
Okay.
So when you say, why can't I do read in parallel with write back? The problem is that the processor also wants to read from the cache. You're also reading from the cache to post it into main memory. So even if you have a read and write ports, and you will have is my thing, I have to go back to Patterson and Hennessy probably for that, for computer organization. But my guess is that every cache will have read and write ports. And but here both are trying to do a read access on the cache. Therefore, it can't be done.
Okay.
I hope that is correct answer, and also that it makes it more clear why it can't happen. My answer last week. Okay, what's your new question?
Sorry, I missed it, but what is the question actually?
His question was, he said when, like, I was talking about the write back cache, and I said when you're doing write back, the read cannot proceed from the cache. So therefore, they actually copy the data into the write buffer and then put the write back in the background to improve the performance with write back. So he said, why can't I proceed with read concurrently with write back? Why should I put it in a write buffer? Some of these questions, I think, partly come from organization. So I haven't read that. But I did look up some material, or I checked on the internet. Read and write ports are there for the cache that I could see. And then this was my explanation. So Fatin, what is your question?
Oh, ma'am, the questions are like some in the video you sent for optimizing cache performance. He explains how he drew some graphs to indicate the change.
Okay, associativity. Yeah, things that's true. In fact, I haven't started the optimizations. That is the part I'm starting today. I did wonder whether I should even put up the 3rd video from Bhaskar and Raman before I talk about those things. I mean, it's a very confusing model of teaching, right? It's becoming difficult for me also to figure out what should I do, what should the video do, what should you do. And that's also one reason why I wanted some feedback from you people today, because I have no idea how this model is working and how well it's working and all that. So Bhaskar and Raman's 3rd video has some material which comes with the next chapter also. Okay, but I'll be talking about some of those aspects today. We can talk, like, for example, if you increase associativity, right, the miss rate falls. Okay. But what happens? The fall, it sort of becomes a plateau after a point. Okay.
Yeah.
So let me take the whiteboard. Maybe you can help me if, since you have seen the video. The miss rate keeps falling, and then it sort of tapers off, right? It's something like that. So this is increasing associativity, right? It is increasing, and this is the miss rate. Okay, so the miss rate falls, but at some point, what is the point? It is 8-way associative cache, which is equivalent to the fully associative cache. That is what they have found with experiments.
Yes.
So it does not make sense to go beyond 8-way associativity because you're not going to reduce miss rate, but what you're going to do is to increase the hit time. Right? Why you increase the hit time? Because now you have to do tag comparison of all the blocks if you're fully associative.
Yeah.
Whereas with 8-way, you have to compare 8 tags. So you would rather go for 8-way, where at least you have reduced the, of course, the circuitry is reduced, the power consumption is reduced, the hit time is reduced. All these happen as compared to 8-way versus fully associative, and you're not achieving any better miss rate. So you don't need to go beyond 8-way associative mapping. That is one of the lessons that you come across in quantitative analysis of, So there is one I think he talks about. I haven't seen his video recently. So what other things does he talk about?
He compares the miss rate and the miss rate and block size, I think. The variation of miss rate with block size. And he gets a U-shaped graph.
Oh, I think that must be miss penalty, miss rate versus miss penalty also. Yeah, miss rate only. Yeah, block size also. That's true.
So are all these data experimental or like?
Yeah, they have done a lot of, those spec tests that they talk about, spec benchmarks. They are the tests they do on, these are simulations actually they do also before they do the hardware, because once you do hardware, it's very, very difficult to change anything. In fact, the hardware process is a very long and tedious one. And if after you manufacture the chip, you find something is wrong, then, the whole cycle is completely wasted and you are set back many years. So people are very, very careful when doing hardware, unlike software where we actually do with such a buggy software and have no problem about it. If there is even one small bug in hardware, it's a problem, right? Cisco actually has the reputation that not a single hardware chip has failed so far. And it's supposed to be a very, very incredible record. People say it's very difficult to achieve that sort of a record. So what they do, in fact, you will see in the memory hierarchy chapter, at one point he talks about a software called Cacti, where they do a lot of CAD simulations of the hardware. And after they are comfortable with the results, then they start actually going into the hardware. So the problem is when you increase the block size, right? After a point, what will happen? You will actually bring in large blocks into the cache. Cache will not be very large, right? You're not increasing the cache size. You're increasing only the block size. So, if the spatial locality is there, but it will not be there infinitely, right? So the larger blocks will mean when you go out of your spatial locality, then you will actually have to fetch a new block also, right? So that's one thing. Second thing is that fewer blocks can be brought into the cache. So again, it's to do with locality. Supposing if your locality is not so good and you're bringing in fewer blocks, then every time you have to go to a new block, you'll have to replace some block here, and that will increase the miss rate also. So there is a point up to which the block size reduction will help your miss rate, beyond which the capacity of the cache versus the block size, that trade-off will result in higher miss rate. In fact, one possibility I was also thinking was, should we play some of the videos while doing these sessions? But that's a waste of time, isn't it? Okay, these 3 C's of misses, I think you know. Should I have explained them? Because they are in Bhaskar Raman's first video itself, I think. Or compulsory misses, right? When you first start a program, nothing is in the cache. So every time you have to fetch something which is in a new block, it will be a miss. You can't avoid these, right? You have no choice but to put up with this. So these are compulsory misses. What do you think will reduce compulsory misses? And is there something which can reduce compulsory misses? Not really, right? And capacity misses is basically the size of the cache, right? What is working set size in operating systems that you studied? Because I said here programs behavior, that's what I'm saying. Okay, memory application needs, can you be a little more precise about how it's defined? Because I said capacity misses depend on the size of the cache and the program's behavior. Okay, what do I mean? Why should programs behavior matter?
Is it just a memory required by an application to complete the computation?
I mean, like, but it is the memory requirement of the program, but does it mean the entire program executable memory?
To keep the program running, the amount of memory required.
How do you define thrashing in terms of working set size?
Caching.
Thrashing.
Thrashing.
I mean, again, that's a term you must have read immediately after working set size in memory management in operating systems. Thrashing.
Working set is the number of pages which are required to run the program actively.
Minimum number of pages required for the program to run, right? So now the same thing, you can think of it as working set size should be in the cache, right? Then what happens? If your working set size can fit into the cache, then there is no thrashing in the cache, right? So that is the reason why. That's the reason why I said program behavior will also determine capacity misses. Okay, size of the cache, yes. Even if you increase the size of the cache, or you thought you have increased the size of the cache, but your program's working set size exceeds that, then you have to keep moving from main memory to cache. Whereas operating systems define thrashing in terms of page faults, right? Your pages are not in memory, and you are basically doing page fault repeatedly. That is the reason why you thrash when you talk about main memory versus disk. Okay, when you're talking about caching, you talk about the thrashing between cache and the main memory. Okay, so that is the thing. And conflict misses, because if you are talking about a fully associative cache, then there are no conflict misses, right? Because you can place the block anywhere in the cache. But when you talk about direct map, the conflict misses will be higher. Whereas in set associative map, it will be fewer, because even you can fit it into any block in the set. So you're reducing the number of misses which are due to conflicts when you go for set associative mapping. Okay, that should tell you why your miss rate reduces with set associative mapping, right? Capacity misses cannot be reduced. Capacity misses, if you increase the cache size and you have direct map versus set associative mapping, the only misses that you can now deal with will be the conflict misses, right? So the conflict misses are better handled in set associative mapping, because of which your miss rate reduces as compared to direct map. Okay, I know we got a 5-minute lesson, so now we have another 4 minutes, I think. So when we look at the average memory access time equation, which I did in the previous session, average memory access is basically equal to hit time plus miss rate into miss penalty, right? So if there are 3 terms in that equation, so you can come up with optimizations which target each of those 3 terms. So you can either reduce the miss rate, you can reduce the miss penalty, or you can reduce the hit time. And that's basically, okay, I don't know now. The animation which works in a computer is not going to work here. No? What am I supposed to do? I greatly put up a lot of animation in this. Anyway, so okay, this is the thing. Optimizations to reduce miss rate are 3. These are basic optimizations we are talking about, right? This is chapter appendix B. When we go to chapter 2, after this, there are 10 more optimizations that we talk about. So this chapter talks about 6 optimizations for improving the cache performance, and then chapter 2 talks about 10 optimizations for improving cache performance. So overall, we look at 16 optimizations for cache performance improvement. So increasing the block size reduces miss rate, like we discussed a little while back, up to a point, and then it increases again. So there is no point in reducing block size where miss rate increases. What else will happen when you increase block size, other than decrease in miss rate and maybe then an increase in miss rate? Okay, so that's a U-shaped curve that you may get. But what else happens to the terms, other 2 terms in the equation? Any idea? Only 1 minute left. Okay, thank you. I think what I want you people to do, we'll break now. Think about this question. When we rejoin, please answer that question. How does increasing